quantum entanglement, and I guess in Professor Panigrahi's group. Yes. Okay. So please take over.
You can see my screen, right?
We can. Sure.
Yeah, thank you. So, today I am going to present like some of our overview of our work. This is the overview of my presentation. First, I will start with generalized entanglement measure for both the discrete variable system as well as the continuous variable system. Then I will move to the two-mode photon array case state. I will discuss about its non-classicality by using photon number distribution and sub-Poissonian statistics, and then we will discuss about the entanglement. So before that, I will give a short brief background of the entanglement measure. Now the question is, what is entanglement? Entanglement was originally called by Schrödinger, the statistical correlation between any two subsystems in a quantum system. There are many entanglement measures are defined to measure entanglement in quantum systems. Here I have described some. First one is entanglement measure based on distances. It says that the closer the state is to the separable state, the less entangled it is. It is defined as the minimum distance between the given state and the set of the separable states. And the next one is the Smith number. Smith number is defined as the minimum. It defined as the minimum is taken over the measure is defined as the minimum is taken over all decomposition of the state, and the Smith number is the number of non-zero Smith coefficients, and if the Smith number is 1, the state is separable, and if the Smith number is greater than 1, the state is entangled, always entangled. Now let's come to the concurrence. So concurrence is a famously used measure to quantify entanglement in a bipartite system. It was first introduced by Hill and Utters in the 90s, and then if the concurrence is 1, the state is maximally entangled, and if the concurrence is 0, the state is separable, and if the concurrence is between the 0 to 1, it is entangled state. Now let's come to the negativity. Negativity is also a popularly used measure to quantify entanglement. Negativity vanishes if and only if all the eigenvalues of the reduced density matrices are non-negative. Now the non-vanishing value of the negativity indicates the entanglement. Now the question is, we already have so many entanglement measures. So now why we needed new entanglement measure? The new measure is requires a less computational effort in our measure. So now we'll discuss about the new measure. So in our measure, we have defined that the entanglement measure is defined as the voice product between the post measurement vectors. So now here the separability and entanglement across the bipartition geometrically corresponds to the post measurement vectors being parallel and non-parallel respectively. So this approach is much simpler and transparent as compared to the other approaches. So now next this is for the discrete variable case. Now you next ask the question like, can we define this measure in the case of the continuous variable systems? So here in this work, we have proved that even if a single pair of elements of a continuous variable case, like in infinite set of vectors are mutually if they are not mutually parallel, then this adds entanglement to the system, and we then express the condition of separability by using the extension of the notion of the voice product, and we derive the geometric measure of entanglement by using the extension of the Lagrange identity for the continuous variable test. Next we extend this concept to the mixed continuous variable case. Mixed continuous variable case by using the convex loop construction. And for convex loop construction is a general method to define a generalized entanglement measure for a mixed test. Now we have also proved that the measure is a good measure of entanglement. We satisfy all the criteria. The generalized entanglement measure is 0 if the state is separable. It satisfies all the 3 criteria. First one is the generalized entanglement measure is 0 if the state is separable, and the second one is the measure of entanglement is invariant under the local unitary operations, and the third one is the measure of entanglement cannot increase under local measurement and classical communications. And then we also have proved that we showed that the entanglement of phase mass squeeze test. We compared the entanglement of phase mass squeeze test with the squeezed vacuum state, and we proved that squeezed vacuum state is more entangled than the phase mass squeeze test. Then we asked the question what happens if we add photon on 2-mode cascade if the both modes are independent? And now the cascade is the superposition of the coherent state, and here we added photon, means we added creation operator on first mode and second mode independently, and after some calculation we get the photon added 2-mode cascade. And here we prove its non-classicality by using photon number distribution and sub-Poissonian statistics. And the photon number distribution is defined as the oscillation. Here the oscillation in the photon number distribution shows the non-classicality. Here photon number distribution is the probability of finding Q1 photon in the first mode and Q2 photon in the second mode. Now here we observe that we showed that for different phases, photon number distribution for different phases, for phase is equal phi is equal to pi, and then phi is equal to pi by 2, and then phi is equal to 0. And one interesting thing here we have observed that the region we shows the photon number distribution is shifted away from the origin. So now we again prove this non-classicality by using the sub-Poissonian statistics. Sub-Poissonian statistics is another method to prove non-classicality. In order to understand the sub-Poissonian statistics, we first have to calculate the Mendel parameter, and we says that the Mendel parameter is negative, it is sub-Poissonian statistics, and if the Mendel parameter is positive, it is Poissonian statistics, and if the Mendel parameter is 0, it is if the Mendel parameter is positive, it's super Poissonian statistics, and if the Mendel parameter is 0, it is Poissonian statistics, and coherent state follows the Poissonian statistics. And here in this figure, it shows that a Mendel parameter here plotted the Mendel parameter with respect to alpha 1 and alpha 2, which implies that the introduced state is non-classical. Here the Mendel parameter is negative with respect to alpha and alpha 2, and so we have proved that the introduced state is non-classical. Then we come to the entanglement. We have calculated the entanglement by using concurrence for the introduced state, and here we observe that the introduced state is entangled, and when we increase the number of photons, the state is become more entangled. So here here you can say that the state approaches to approaches to maximally entangled after increasing the number of photons. These are the basic overview of my work, and here some like I have just presented the basic overview, and this is it. Thank you. So if any questions, you can ask.
Okay, so thank you, Nibedita, for nice talk. So is there any question?
So can I stop sharing?
No, please keep it there. If somebody asks,
Yeah, sure.
you have to show the slide. Okay, Subhayan,
Yes.
please.
Oh, yeah, thanks for the talk. So on
Yeah,
slide
thank you.
you wrote something. If there's time, I just want to parse that. So on slide 4.
Cell type 4, yeah.
Yeah. So there you sort of wrote about this equation. I was wondering, how do you select the phi's? So I'm guessing the psi is the state whose entanglement you want to check.
Yeah. Actually, these are the post measurement vectors for the continuous variable space. Like, yeah.
Maybe the discrete version, the first equation you
Yeah,
have here.
first equation is the discrete version, and second equation is the continuous version. So these are all the post measurement vectors, and after taking the voice product and Lagrange identity, I've written the formula, and you can find all the calculation in the second paper here, 2022.
Right. But now that you're here, I can ask you quickly.
Yes.
So when you say post-measurement state, so is phi like the computational basis or like a canonical basis? Like measurements are
canonical basis, or since this is continuous variable case, and we have taken the condition here that the in the orthonormal basis, like phi and the expectation value of phi and psi is 0, and if you understand my point, right? It is expressed in the orthonormal basis.
But how do you know the phi? How do you know how do you choose your basis? I think that's
for continuous variable cases, and we have to follow the condition like the orthonormal basis. So if it follows that, then we can find the entanglement. If it doesn't follow that basis, then maybe we can't able to find. Maybe that is not proved yet, but till now maybe we can find the entanglement if the basis is not orthonormal.
I think now I definitely want to look at your paper. Thanks. Also, one last question, if you have time.
Yes, we have.
Entanglement measure, is this defined for bipartite systems or multipartite?
Yeah. First for discrete variable system, it is for first we have defined for bipartite system. Then we extend to the multipartite system, and for the continuous variables case, it is for the multipartite systems. And you can also find entanglement for bipartite system, but it is more easier for the multipartite case. Like in other measures, I can explain more if you want.
Thanks.
In other measures, like for multipartite case, it is difficult to find the reduced density matrix by using by using like concurrence or negativity and other modes. But here in our measure, it is much more easier and efficient to find the reduced density matrix of the state. So, and it needs less computational effort, and also less time to find the entanglement. Yeah, any more questions?
Yeah, please ask questions because we have some time, and please unmute yourself and ask the question directly. It's better than typing in the chats.
Yeah, actually, Abhishek Misra is is present now. He was presenting, but he's not here. So I'm just presenting my works. I have not prepared well, but
No, that
so
is fine,
just,
and that
yeah.
that is fine. At least the information is there, and you are citing your work so people can follow.
Yeah.
But the slot is another 10 minutes is left in the slot, so we can have more questions if needed.
Yeah, sure.
If people want to ask, and if the speaker is willing. And in the meantime, I would like to request the speakers, mainly the previous speakers, if you can, if you are still available, if possible, just go to the chat, and if you see some questions relevant to your talk, which you have not answered during your talk, you may find the liberty to just type the answers if possible for you. Like it will save time, I guess, or maybe you can come back later also, whatever you like. So can we have some more questions? Okay, yes, sir, please come on.
See, I have a very general kind of question.
Yes, sir.
See, just to sort of think about it. And
yes,
see, if you see what we have got in this measure is something like, square of the eigenvalues, C square, if you see, and it gets related to area.
Yes.
But we know there are, invariants in geometry, like Patra was talking about, volume. For example, if you take a matrix, it has trace of the eigenvalues. So finally, everything is eigenvalue. Square of the eigenvalue, cube of the eigenvalue. Each of them is a measure. Very recently in density matrix in chemistry, they're relating to this higher order invariant to subtle properties of materials like the golden glow of the many materials comes through this kind of invariance. It's worth thinking beyond the square, beyond the area.
Yes.
Other kind of things if one can interpret physically later on. It's not immediately, but later on.
Yeah, sir. We can express the entanglement for higher dimensional cases in terms of ellipse and something like that. But it needs some topology kind of thing. So we have to think more about it. So
sure.
Yeah, we should think about it. Thank you for the.
Sir, if I may, this area is the area interpretation is coming out of this wedge product, right?
Sure. Yeah.
So means for higher dimensional area like volume or hypervolume, you will be needing more products. You can think like that, perhaps.
Yeah, that would be that is definitely one way.
Because
particularly think in terms of what Patra was talking about.
Yeah, can you comment
manifold,
on this? Yeah. Can I comment on this?
Yeah.
Yes, please.
Yeah, actually, something like quantum tomography. So here, there is like you need less number of less number of what do I say? Less number of states to present your entanglement. So if you consider more number of some states or more number of particles to present your entanglement, then the entanglement you propose that is not more efficient and more valid. So we need to have so that's why.
So you mean to say the area is more economic rather than volume or something? So maybe
volume can be more economic, but we have to consider less number of particles to present volume. So we can that is.
Okay.
Yeah, Kumar, I have a point also. What she said. Yes. See, I am thinking more in terms of the Bergman invariant, because if you see the area is like very phase, right?
Yes.
If we are comparing two vectors, but if you see Poncharatnam phase or Bergman invariant, sometimes they compare three vectors, parallel transport. Those are the kind of things I'm thinking about. Yeah.
Okay. Understand. Okay. Okay. Then thanks for a good discussion. So actually what is happening, we are still 5 minutes ahead of schedule. But still, if there is no more questions, we can thank Nibedita for the nice talk. And
so I will stop sharing.
yeah, you can. You can very much.
Yeah,
Please.
yeah.
So next speaker is I think Nilakanto Meher. But the point is that we are early in the schedule. So is he available for the talk? Mr. Meher?
Yes.
Okay.
I'm available. Enough.
Okay. So you are ready to start?
Yes, I can start if
yeah.
all are,
Okay.
ready to listen, definitely.
Okay. Yeah. People are ready to listen. Like it depends on your. So thanks for, yeah,
Okay.
let me just introduce you a little bit. Thanks first to start 5 minutes early to make the schedule without gaps. So we have Dr. Nilakanto Meher, who is now working in Weizmann Institute of Science. He specializes in quantum entanglement, and I just give the podium to him. Thank you.
Yeah, thank you, Avinav. And I really thanks to Professor Panigrai sir and for giving me this opportunity. So my screen is visible?
Yes, it's very much
and
visible.
Am I audible also?
Yes, very clearly. Very clearly. Thank you.
Okay. So I am at the full screen. So today I'm going to present direct measurement of atomic entanglement. So I'll start from what is entanglement. Then I will say what is the most used quantifier generally we use to quantify the entanglement of a 2-qubit state. And I will propose a setup for measuring this entanglement between two atoms. Essentially 2-qubit state. And this scheme involves essentially cavity and mostly atom cavity interaction. And we'll see how we can quantify or extract the information about the entanglement from zero time delay second order coherence function. I'll explain what is the zero time delay second order coherence function. So let me say a brief on quantum entanglement. So we know in quantum mechanics, state of a single particle is represented by a state vector psi, if it is pure. So if there are two particles, suppose they are in the state psi A and psi B, then combined state you can write in quantum mechanics that tensor product of psi A and psi B. And this is called product state. Let me give an example. If there are two polarized photons and first photon is in the horizontally polarized, that is represented by 1, 0. And if the second photon is in vertically polarized, represented by 0, 1, then we can write the total combined state HV, that is 0, 1, 0, 0. And we know the state of individual particles here. The photon of the first photon and second photon. Now coming to the entanglement. So we know that entanglement is essentially a non-local correlation between two quantum particles. And we write the state psi AB. So what is the definition, mathematical definition? Combined state of the particles cannot be written as a tensor product of the states of individual particles. That means I cannot write the psi AB as a tensor product of psi A and psi B. If where psi A is the state of the first particle and psi B is the state of second particle. That means it is not possible to define the state of individual particles here. So let me give an example here. Suppose this is the combined state of two particles, okay, where 0 and 1 are the computational basis. As I am going to talk about atoms, so let me write this same state here by replacing 1 by excited state atom E and 0 by ground state atom G. So there are two level atoms where the energy levels are represented by excited state E and the lower energy levels is represented by the ground state G. So this is a 2-qubit state. So on measurement, you can see if the